So the question for us now is, what are the practical implications of some of these statistical theories, right? So central limit theorem, great. What does that really mean for us? What does it mean in terms of our ability to infer things about the population from our statistics and our statistics that describe our sample? And the first thing has to do with the mean. And so when we're trying to understand the mean of a population, the question is, can we use our sample mean as a good estimate of the population mean, right? Are they the same? Can we just say, well, if the mean of our sample is this, that's a good estimate of the population? And the answer is yes. Actually, the sample mean is an unbiased estimate of the population mean. This follows out of the central limit theorem. Now, this is because the sampling distribution of the mean is normal. Right, and this happens if either our sample sizes are greater than 30, relatively large sample sizes, or if our underlying population is normally distributed. Why this is important is because it turns out that our population itself does not need to be normally distributed. And if it's not, then all we need to do is take sufficiently large sample sizes from it, and then the sampling distribution of the mean, rather than the sample, the distribution of the variable itself, is normal, which then allows us to say that the mean of the sample is an unbiased estimator of the population mean. What this means is, as I take more and more samples, the error, right, and the error being the sampling error, where my mean of my sample is different from the mean of the population, right? So that's going to happen, right? We're going to have a sample, we'll have a population mean, which is unknown. We'll have a sample mean, which is known, and is probably going to be a little bit off just by chance alone. As I take multiple samples, that mean will shift around the population mean to the point where any error goes to zero. And so the central limit theorem tells us that we can actually use the sample mean, we can infer the population mean from the sample mean by virtue of the fact that that sampling error goes to zero over time. It's an unbiased estimator of the population mean. Now, we use confidence intervals to help remind us that that point estimate is not right. So it's not exactly equal to the sample mean. But from the sample mean, we can create an estimate within a confidence interval that we know the mean, or it seems very likely that the mean is within the brackets around that estimate, right? We call that the confidence interval. So we know approximately what the mean of the population is, or at least we believe or are relatively confident that the mean of the population is based on the sample mean. So that's the first thing. Sample mean is an unbiased estimator of the population mean. That falls out of the central limit theorem. And particularly if we are willing to accept a confidence interval of the mean, then we can be relatively confident that we know close to what the actual population mean is from any particular sample, especially if we have a larger sample, by which I mean 30 or more. The larger the sample size, the more likely that the sample mean is relatively close to the population mean. That's something else that falls out of the central limit theorem, is that sample size really does help us to have a even better estimate, to reduce the amount of sampling error that is going to happen. So that's regarding the mean. There's also some implications regarding the variability of the population, right? And so the question is, if we can estimate the population mean from the sample mean, well, can't we just estimate the population standard deviation from the sample standard deviation? And the answer to that is no. Actually, it is a biased estimator, which means that we cannot just take the sample mean and say the population mean must be something like this sample mean. Or excuse me, the population standard deviation must be something like this sample standard deviation. The way we can do it for the mean, if I have a sample mean, I can say the population mean is somewhere around this. But if I'm talking about standard deviation, the variability of the population is related to, but not perfectly and not unbiasedly estimated by that sample standard deviation. I actually need to correct for sample size, right? And so this is where I bring in the concept of standard error. And so the standard error, which is the standard deviation of the sample divided by the square root of the sample size, is actually a better estimator because it is more useful to me because it describes the variability of the mean. Why is this important? Because when I am estimating the mean. And and really what I want to look at is when I'm looking at statistical significance, when I'm looking to see if my sample is part of a population, I want to look at the normality of what's going on, right? And I want to look at that normal distribution of the sample means. So if I know my population mean and I have a sample, I can compare the sample mean to the population mean. And if it's too extreme, which I can use standard error, the standard deviation of the population divided by the square root of the sample size, I can use that standard error to tell me if my sample mean is too extreme from my population mean and therefore must be part of another population. I can't just use the standard deviation of the sample, or I can't just use the standard deviation of the population. I use the standard error, the standard deviation divided by the square root of n, which is the sample size, in order to make that determination. So again, what are the fallouts here? One, the sample mean is an unbiased estimator of the population mean. If I'm willing to accept a confidence interval around that sample mean, then I even have more confidence that I know that the population mean is somewhere in that. The larger the sample size, the better the estimate of the population mean is. And if I'm going to see if my sample fits into some larger population, I can use the standard error of the mean, which is the sample, or excuse me, the population standard deviation divided by the square root of n. I'm losing my train of thought. The standard error of what I'm doing is I can use that then to tell me, am I in a normally distributed mean, sampling distribution of the mean? Am I too far away from my known population mean? So I have to say my sample actually comes from a different population. So those are the practical then impacts of the central limit theorem, and understanding how from our sampling we can make inferences about our population and about our relationship to a population.